Hey there, good morning team. Chemistry coach coming at you. Let's apply some more of our valence shell electron pair repulsion, although it should be VSEPR valence shell electron group repulsion theory. Let's apply this to complex molecules and species. All we've done so far is look at simple species with only one central atom. Even though we went from 2, 3, 4, 5 up to 6 electron groups, we started getting some of those weird expanded octet shapes, square pyramid and T-shaped and seesaw, which are really cool. But now let's look at things you're going to run into more in organic and biochemistry. So this right here will be one of the top 2, I think, videos if you're planning to go into biochemistry or organic chemistry, because obviously the foundation is the carbon chain, right? So you're going to spend a whole year in organic learning about the chemistry of carbon. So carbon atoms can connect together in a myriad of ways. And you can put, you got hydrogens and you could put nitrogens and sulfurs and things in there. But carbons, I mean, I've never seen a carbon disobey the octet rule. I've always seen a carbon with 4 bonds. Occasionally you run into weird things, maybe a carbocation or something where it's got 3 bonds. But at least in my class, carbon's going to be really nice and follow all the rules. Octet rule, going to have 4 bonds, whether it's 4 singles, 2 doubles, a triple single, it doesn't matter, whatever combination. So these complex molecules, again, the definition of a complex molecule means it has 2 or more central atoms. It's no longer simple. The issue with applying VSEPR to that, right, you should be able to do the Lewis structure, and we did some crazy ones when we did Lewis structures. Review that if you need to. But now we've got these central atoms connected together. VSEPR applies to an individual central atom. Okay, I guess you could apply it to a terminal atom too, but it's kind of weird. We'll need to do that for the model sets we're going to be doing later. But at least for now, we're going to focus on the central atoms, connect them together, apply VSEPR to the first central atom, and you'll get some kind of molecular shape, whether it's tetrahedral or trigonal bipyramid, whatever it is. And then you look at the second central atom. Look at the number of electron groups, apply VSEPR to that, and then connect the first central atom to the second central atom. If you have a third one, apply VSEPR to that individually, and then connect that to the second one. And you try to work left to right across your page, because it can twist and turn, single bonds can rotate, so depending on where you put the second central atom, do you connect it here or here, you can meander up, down, you could go across and down. They're all correct. They're just called conformations, but we're going to try to get it to work across your page. So watch how I apply it. Nothing new today. We're just connecting the central atoms together. That's the key. And then we can apply, so you can't really get a molecular shape overall of a complex molecule because you got too many central atoms. But we can look at individual atoms and go, are those in the same plane and these ones aren't? So we'll use the dash wedge, which is a VSEPR structure, is a dash wedge structure. So you can use the dashes and wedges to see which atoms are out of the plane, and you can use the lines to show which ones are in the plane. So you could count through a complex molecule and go, well, there's 8 atoms that are in the same plane, and then there's 3 that are sticking out towards your face and a couple going away from you. So it's a little more limited in that, but it gives you a rough idea of the overall 3-dimensional molecular geometry that's happening for this particular structure. That'll be real important. So let's just get to it. Review your rules for Lewis structures. Let's work through 2 or 3 examples. Won't be a 2, you'll kind of see after the second one, it's the same pattern over and over and over. So let's go do it. Let me put one up on the board for you. Here's your first one. So let's do the Lewis and the VSEPR structure. So I want to show you the difference where the Lewis structure just shows the connection of the atoms. Nothing to do with the shape. Although the more you do this, the more your brain starts thinking VSEPR immediately. So a lot of your Lewis structures tend to reflect the bond angles, right? But we don't do the dashes and wedges for the Lewis structures. So I want to show the Lewis and VSEPR structures side by side. So go ahead, look at this molecule. I want you to calculate the number of valence electrons, do the 6n plus 2 minus number of valence electrons, see if there's any double, triple bonds, electron deficient species, expanded octets, all that fun stuff. Pause it, take care of that, get at least the Lewis structure done. Let's see if we match. And then if you are feeling daring, go ahead and try the VSEPR structure and see how that works. So let's walk through this together. So for the Lewis structure, so we want to calculate the number of valence electrons, so we could probably count that up. I'm not going to go through the whole thing together, but we got 4 5, 6, 13, 17, 17, 18, 19, 23, 30, right? So we got 30. Normally I would draw that out. You know, we got this many carbons and that many hydrogens, but just go 4 plus 1 plus 1 plus 7 plus 4 plus 7 plus 4 plus 1 plus 1. That's usually where I screw it up myself. All right, so let's do our 6n plus 2. And n will be 1, 2, 3, 4, 5. So that'll be 32. So if we subtract those, so we've got 32 minus 30 equals positive 2. So we've got a double bond. There's not enough carbons in there for a ring. We know we don't have boron, beryllium, or aluminum, and we have an even number here, so there's no electron deficiencies. So it's got to be one multiple bond, which would be a double bond in there. So let's go ahead and draw it. So we know that those two hydrogens are on that carbon, and this bromine is on that carbon. We know this fluorine is on that carbon, and those hydrogens are on that carbon. So use that condensed structural formula for that. So let's start with that carbon. Get the two hydrogens. Get the bromine. Doesn't matter. You can put the bromine here or down there. Doesn't matter where you put it. And let's connect that to carbon number 2. So we got carbon number 1 with the two hydrogens and the bromine. Carbon number 2 with a fluorine. And you can put that up or down, but I want to work this to the right, left to right, connect that to the next carbon. And that has two hydrogens on it. And you could have put one here, one here. Doesn't matter where you put them on that atom, top, bottom, right, or left. That's irrelevant. So this is what we're left with. We need to place a double bond in there. Can't go to the first carbon because that already has 4 bonds. That would disobey the octet rule. This carbon has 3, that carbon has 3. It can't go to hydrogens. Fluorine prefers 1 bond, so it doesn't want it. So it seems pretty obvious to me that double bond has to go there. So now that carbon has 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Octet rules. This bromine needs some lone pairs, right? 2, 4, 6, 8. There's our Lewis structure. Hey, hey. Okay. So now we can do the VSEPR structure. Let's do it over on this side. Which, again, you could call that a VSEPR structure, or you could call that a dash wedge structure. Doesn't matter. It's the same thing. But when I say draw a VSEPR structure or dash wedge structure, I want you to draw everything with the proper bond angles. Dashes and wedge if you're in 3 dimensions. I want you to give me the molecular geometry of every central atom. Is it trigonoplanar? Is it T-shaped? Those kinds of things. And give me the bind angles, all the unique. So if everything's 109.5 around one central atom, you can just say 109.5. You don't have to do every single angle as long as they're all the same. But if you've got different ones, hi kitty. Let's go ahead and do it. Okay, let's look at central atom number 1. Let's make that a different color. Let's look at carbon number 1. How many electron groups do you see? I see a single bond, single bond, single bond, single bond. So that's 4 electron groups. There's an atom on the other side. So 4 electron groups all are bonding. So that has a tetrahedral electron group geometry. And since they're all bonding groups, a tetrahedral molecular shape. So carbon number 1 is going to be tetrahedral. So let's draw a tetrahedron. So let's draw that carbon. That's a pretty ugly wedge there, dash. So do you see I just drew the basic structure of a tetrahedron. And now it really doesn't matter where you put, but I have a hydrogen up on top. So let's put that hydrogen there. I have a bromine here. So let's put a bromine there. Hydrogen there. And then that'll connect to carbon number 2. You see that? And so I can look through here and go, hey, I'll fumble my blue pen. Bye. So I know that this is 109.5 degrees, right? Actually, all 4 of those angles, the bromine, carbon, hydrogen, hydrogen, carbon, carbon, bromine, carbon, hydrogen, hydrogen, carbon, carbon, are all 109.5. So I'm good just putting the 109.5 degrees there. And this carbon right here is going to be tetrahedral, right? So that's going to be tetrahedral. So let's go here and go tetrahedral. Or you could, if you don't want to do arrows into it, you can just write it separate and go carbon 1 is tetrahedral with bond angles 1 and 9.5, and just make sure you know which one's carbon 1, 2, 3. Right? That's for, as long as it's obvious to me and I can see it, I'm good. Well, let's look at carbon number 2 right here. Let's count the electron groups. Single bond, double bond. The double bond counts as one group, right? I have 3 electron groups. So that's got a trigonal planar electron group geometry. All of them have atoms on the other side, so they're all bonding groups. Therefore, the molecular geometry is the same as the electron group geometry. So that's going to be trigonal planar with 120-degree bond angles. I've already got this one set. So what I do is I just treat that. Normally, I would start with a bond up, a bond down this way, but I'm just rotating it. So this will be my top. Now, you could put the double bond down or to the right. It doesn't matter to me. But you've got the carbon-carbon bond. We're going to have a carbon-fluorine single bond. And you could have put the single bond of fluorine over there. But then you start working down. You see that? I like to get my carbons going, my carbon chain going left to right as best as possible. Not right or wrong. It just fits in the box a little better on your exams. And then there's a double bond to carbon number 3. Remember, in VSEPR structures, you don't have to draw the lone pairs. We're looking at where the atoms are in 3 dimensions. Whereas a Lewis structure, we're trying to see where the electrons are placed. So you have to draw these lone pairs. So you're welcome to, but it's not necessary. I do like to include them if they're on the central atom, because if I don't, then I forget to get the appropriate angles and things. All right, so these are 120-degree bond angles. Everybody agree? So this is 120 degrees. Boop. So all the carbons, the carbon-carbon fluorines, they're all 120. And that would be trigonal planar. Everybody agree? So work on those VSEPR shapes. Trigonal planar. All right, let's look at carbon number 3 right here. That's my last central atom. That has a single bond to a hydrogen, double bond. That's 3 electron groups. So that's a trigonal planar electron group geometry. All of them are bonding, so that's also trigonal planar. So this would be, so make sure you just get the 120-degree bond angles as best you can. So see how I drew kind of the trigonal planar there? And I've got a hydrogen on either side. And then this is also trigonal planar. So instead of writing it twice, I'm just going to draw another arrow. So both of those are trigonal planar. Saves me some space. And then every angle here would be 120 degrees. So that's how you do a VSEPR structure or dash wedge structure for complex species. You just do each, identify your central atoms, apply the VSEPR model to each one in turn, and just connect them. You'll have this dangling bond left over from the first central atom. You just connect the second one to that, and then just do your shape appropriately from there. And there you go. So if you say, what's the shape of that entire molecule? You'll be like, I don't know. I could tell you each individual central atom, but I couldn't tell you the shape of the whole molecule. It's complex, right? But I could say this hydrogen, that carbon, that fluorine, that carbon, that hydrogen, and that hydrogen. So 1, 2, 3, 4, 5, 6, 7. There are 7 atoms in this molecule in the same plane. Anything that's aligned like that, whereas this hydrogen's coming out at your face and that bromine's going away from you. So you could count the number of atoms in the same plane. And if I could rotate it, like take a piece of paper or something and take the molecule and rotate it towards you, all the atoms would be in this plane, except you'd have a bromine coming out here and a hydrogen coming out there. Just gives you a different way of looking at the molecule. Let's do another one. If you can do that, you can do them all. They may be longer. Maybe we'll have 7 central atoms, so it's a big, scary dog that just barks, doesn't bite, right? But you just do each one at a time. You eat an elephant one bite at a time. It's very doable. Try this one on for size. The problem, well, not the problem, the good thing, I guess, from your point of view of doing organic molecules, because most of the time those are going to be the complex ones, cat hair in the mouth, will be the limitations. You don't get expanded octets. I mean, exceedingly rare. You won't get them in my class for organic molecules that are complex. So you're limited to just 2, 3, or 4 electron groups. So you're limited to the linear, the bent, the trigonal planar, the trigonal pyramid, tetrahedral. That's about all you have. So you lose all the cool structures. Let's do this one here. HCCSH. Looks simple. Once you do enough of these, you're like, well, there's carbon again, there's sulfur again, and, you know, likes its particular things. So let's go through and calculate. So let's do the number of valence electrons. So pause it if you can. Try to do the whole thing and see if you get what I get. Even though maybe you drew it, you know, meandering in a different direction, it doesn't mean it's wrong, right? But I try to get you to draw tetrahedrons and things the same way every single time and just connect in a certain way. That way you don't waste time on a test going, trying to picture something in 3 dimensions. You're just like, boom, I've done a tetrahedral 347 times exactly the same way. I've done trigonal bipyramid 347 times exactly the same. I don't know why I keep saying 347. All right, here we go. So I've got 1 plus 4 plus 4 plus 6 plus 1. So we got 8, 9, 10, looks like 16. 16, so it's not a free radical. That would have to be an odd number for a free radical. What's N here? 1, 2, 3, so N is equal to 3. So 6 times 3 is 18 plus 2 is 20, right? So 20 minus 16 is positive 4. I don't see boron, beryllium, or aluminum, and that's a positive number. So I mean, an even number. So it's not an electron deficiency. Only 2 carbons. I can't form a ring of 5 or 6 out of that, so there's no organic ring. So that must be 2 multiple bonds. 2 multiple bonds. Now that could be 2 double bonds or 1 triple bond, just 2 extra lines, right? So let's draw the skeletal framework for this. Obviously, if we look at this carbon is connected to that carbon. That hydrogen's connected to that sulfur. So it seems pretty straightforward. Let's do it. So let's draw the hydrogen bound to that first carbon, bound to that second carbon, bound to that sulfur, and that hydrogen's bound to that sulfur. So hydrogen, carbon, carbon, sulfur bond to the carbon. Well, this seems easier than the other one, actually. But we got 2 extra lines. They cannot go to the hydrogens, correct? So let's see. Sulfur prefers how many bonds again? So you look how many columns away. Sulfur's right there. So 1, 2. So sulfur prefers 2 bonds. So sulfur's pretty happy already. I mean, you could put a double bond there, but the formal charge probably wouldn't be 0, so it wouldn't be happy. You want to get the ones with all the formal charges 0 or as close to 0 as possible. And again, if you're not sure, do the formal charges, see what works. And sometimes you get those weird ones where it's not quite what you would expect, but not on my exams. This carbon only has 2 bonds, so it wants 2 more, but it can't go there. See that? Which means if I put a multiple bond there, one of my 2, that gives this carbon 3 bonds, and that carbon 3 bonds. They're still not satisfied, right? What was that? What did I watch? Was it Fat Albert when I was a kid? Satisfied. He'd walk around going, "Hey, Mabbin, wubba tubba. I'm a fat Albert." It was a great cartoon. And I practiced so hard to get that. "Hey, bubba tubba, Mabbin. Lebbits, some of Trevor's." It's so hard to do that. And hello, how are you today? Wow. Remember, I didn't have computers or video games when I was a kid or cell phones, so you just sat around doing stupid human tricks the whole time, right? I spent hours trying to work on your eyebrows and your ears and doing weird language. Anyway, you didn't need to know that. Here we go. We need another bond there. There's the second multiple bond. So 2, 4, 6, 8. 2, 4, 6, 8. 2, 4. Oh, we need a couple more for the sulfur. 6, 8. Duet rules, octet rules, everything has their preferred number of bonds. Wada bing, wada boom, we've got it. So now let's look at the central atoms. So this hydrogen's terminal, we don't do that. So that carbon number 1, carbon number 2, and the sulfur are all central atoms. Sulfur has bonds to 2 other atoms. So this also has 3 central atoms, just like the last example. So let's take them in turn. Let's do carbon number 1. We'll treat that as our first central atom. That has a single bond and a triple bond. That's 2 groups. That's 2 electron groups, is a linear electron group geometry. Both are bonding groups, so this would be a linear molecular shape. if we do this. So let's draw the hydrogen. So we've got 180-degree bond angles for the good linear structure. And that carbon number 1 has a linear shape or molecular geometry. Let's look at carbon number 2. Oh, I'm getting covered with blue ink or black ink. And then I wipe it all over my sweaty face and be like, ah. So let's look at carbon number 2. We've got a triple bond for one group and a single bond for two. So it's the same thing, 2 electron groups, both bonding. So carbon number 2 is also linear. So this bond will go straight across to the sulfur. And this will also be 180 degrees and also linear. So I'll just write linear once and draw both carbons towards that. So 180 degrees from the hydrogen-carbon-carbon and the carbon-carbon sulfur bonds. Those are both just, so far, this is just linear all the way across. The whole molecule looks linear, but we haven't done the sulfur yet. So let's work on the sulfur now, which is our third and final central atom. I don't think we need to do more examples beyond this. It's just the same thing over and over and over. This should give you enough. And I'm going slow. It's a good review for Lewis structures and things. So this is, if you can do this, you're going to have a great time on my quizzes and tests. And you'll do really, really good starting out. If I was teaching organic, I would expect to be able to do this on day 1. Right? The other thing that we haven't learned yet is hybridization. You should be able to go through and go, SP, SP, or SP2 or SP3, those kinds of things. We'll learn that in the next section. So let's look at sulfur. So I've got a single bond, another single bond, a lone pair, and another lone pair. That's 4 electron groups. 4 electron groups is a tetrahedral electron group geometry, right? But they're not all bonding groups. This is 4 electron groups with only 2 bonding groups and 2 non-bonding groups. So let's draw the tetrahedral shape of the single bond, lone pair, lone pair. So we've already got a single bond. So I'm going to treat that as this. And I'm going to rotate my tetrahedron. So normally I would draw a tetrahedron like this. All right? That's how I would normally draw a tetrahedron. So let's just stick this bond there. Right? So that bond becomes this bond. So I'm just taking this tetrahedron and flipping up on its side. So what's going to happen, or if I had my paper, I'd rotate my paper. So this will come out this way. You'll have an open wedge and a dash wedge. So I just took my tetrahedron and up, boop, like a little bell, ding, 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 and I just connected it that way. And you can put the hydrogen anywhere, but I like to put it here so I can see that bent shape. And these are the lone pairs, which you don't see in a VSEPR structure. So I'll show you some alternatives. You can leave it like that. I'm perfectly fine if you want to leave it like that. But would you agree, for a tetrahedral shape, you get 109.5 degree bond angles? But these lone pairs take up a little extra space, so that's going to be quite a bit less than 109.5. I don't expect you, a lot of people say just subtract 2.5 degrees for every lone pair. That works okay for carbon and things like it, maybe oxygen, but when you get farther down the periodic table, things aren't so nice anymore. So pretty tough to predict the specific bond angle. So I'm okay if you just say less than 109.5. So less than or equal to, or maybe approximately 109.5, but it's going to be less than that, right? That's all we know, because these lone pairs are pushing it closer together. Now that's a tetrahedral electron group geometry, but it's not a tetrahedral molecular geometry because you don't see these lone pairs. So another way you can draw this is get rid of the dash and the wedge. I always like to put the lone pairs there to get rid of them if I can. You can leave it just like that technically, but for me, if I don't put the lone pairs, I want to make it straight and it's not linear, right? So I'll tend to keep the lone pairs there just to remind myself. But again, you could do it with nothing there, the two lone pairs, or the dash and the wedge with lone pairs. I'm okay with all three of those. If you're taking it from a different professor who's more specific, if they're grading your test, do it the way they want it to. It's like when I coach softball or baseball. I'll get, 10, 11, 12, 13, 14-year-old kids coming up, and I'll try to teach them a specific way of running a play or doing something like, but my dad taught me this one. I'm like, if your dad's not the coach, I'm the coach, right? We're going to do it this way because I need a cohesive team. Doesn't matter what you were taught before. I'm the one running the team right now, right? So you've got to do what you're coaching. And your professor is your academic coach. So no matter what I or someone else teaches you, when you move on, learn what they're teaching you. They may say, this 6n plus 2 thing's stupid. That's perfectly fine. Do it the traditional way. I don't care. It's all right as long as you get the answer right. But go with what your coach is doing at the time, all right? But there's 99% of it's going to be pretty similar. What is the shape of this? That sulfur is bent or V-shaped or angular. I've seen all three of those, but bent seems to be the most common. There you go. Linear, and it's not a linear molecule because it goes, click. But would you say this is a planar molecule? Yes. See, those are all alike. The dash and the wedge. The lone pairs stick out like this, but we don't worry about that in the molecular geometry. So all five of those atoms are in the same plane. So I can't say this is linear, but I could say this is a planar molecule. All right, we got it. You can do anything as far as Lewis and Vespers structures. You guys got this.